All right, AP, last video for the chapter, but it's a big one. 15.7 is a principle called the Chatelier's Principle. Obviously after a French scientist that he studied what happens if you disturb equilibrium and how do you fix it. So we got some big learning objectives here. One, can you identify this thing called about external stress? And then talking about K versus Q. Okay, so 15.6 was about K versus Q. And then now we're going to learn about what happens if you mess with equilibrium. How do you get K to equal Q? Okay, so let's get started. Take a minute, read the learning objectives. This is big, okay? Because you're going to see this topic, K versus Q, in a couple other chapters coming up, okay? All right, annotate, highlight, make some notes, and here we go. Suppose that a chemical reaction was already at equilibrium, okay? So what do we know back from the beginning of equilibrium? So that means that the rate of the forward, so K forward, is equal to the rate of reverse. So remember, rate is chapter 14, kinetics. Be very careful with your K's when it comes to equilibrium, okay? So at equilibrium, your rate forward and your reverse are the same, okay? Your concentrations or pressures for the reactants and products are no longer changing over time. But remember, it does not mean that they are the same, which I think we saw with ice charts, okay? So what would happen if a system that was at equilibrium experiences some sort of external stress, okay? So what the heck is this external stress? So Le Chatelier came up with the principle, okay? He said that if a system was at equilibrium, but then it got disturbed, okay, aka experiences an external stress, the position of the equilibrium shifts to relieve that stress, okay? So how are you shifting left, right to relieve that stress? You won't go back to the original equilibrium. You'll have a new equilibrium, and I'll show you with the picture of what that actually looks like on the equilibrium graph, okay? So this shift to relieve it is going to give you a new equilibrium. So what type of stress could you have? You could have a change in concentration, a change in pressure or volume, and you know the big one, change in temperature, okay? So we're going to look at all three scenarios, do some sample problems with it, but take your time. This is the big one. This is the explaining chapter, okay? Our normal equation that we've been using this whole chapter, 2NO2 produces N2O4. So we know our Kc, our equilibrium, is our products of the reactants. And because there's that 2 in the equation, we're going to have that order of 2. Let's say this. We add more reactants, okay? So what happens is, remember at equilibrium, we want our reactants and products to be constant. Not the same, to be constant, okay? We want both the rates to equal each other. But what happens if you add more reactants? So what happens is my little teeter-totter, reactants just got dominant, very, very dominant. And remember, we're assuming that temperature is not changing, okay? So what happens is you apply a stress, okay? You apply a stress by adding more reactants. So the reaction is no longer at equilibrium. So now you're solving for Q, okay? So you're no longer at equilibrium, so how do you fix it, okay? So let's remember from 15.6, okay? If your K equals Q, then you're at equilibrium. But we're not at equilibrium because we messed with equilibrium, okay? So if I have too much reactants, okay, so right here, my K is greater than my Q, I don't have enough products, okay? I have too little products and too much reactants, okay? So if I have to fix equilibrium, I'm going to have to shift to form more products. And by shifting, I'm going to have to shift to the right because that's where the products are. And by forming more products, I'm going to get a new equilibrium. And now that's shifting to the right, so that way my K equals Q, okay? Or vice versa, okay? If I have too little reactants, too much products, okay? I'm going to have to form more reactants to shift to the left and so forth, okay? So notice what happens, okay? So this was Kc. That was that equilibrium. You added, who's our NO2? Sorry, my equation up there. We added reactants. And notice what happened to the denominator. It got bigger. That should make sense, okay? Small number, now over a big number, what happens to my Q? Well, my Q decreases, okay? So that's why my Q is less than my K, so my K is greater than Q. And remember our cool little trick. Pretend like you have that little arrow that's trying to point you on how to fix equilibrium, okay? So what I did for you is I wrote you the beautiful explanations that you need to tell AP on what to do. So there's 3 components. So to achieve equilibrium or to re-achieve equilibrium, the reaction, and actually I'm going to put to re-achieve because we were at equilibrium, but now we got to re-achieve it. I'll fix those in the notes. The reaction must, how are you going to fix it? Which way are you going to shift? And why are you fixing it? Okay, so I got to form more products. So that way I got to shift my equilibrium to the right. And by shifting to the right, I'm going to get my K to equal my Q. Okay, so remember, I'm going to have a new equilibrium. So what does that look like by adding that stress to the curve? Okay, so remember, we added some NO2. And remember, my NO2 is a reactant. And what happens, oops, put that there. What happens to reactants over time? Well, they're disappearing over time. So I had equilibrium, so this was equilibrium, flat line. And then right here, the change is made. I added, oops, that stress. I added that stress, that's supposed to be an S. And what happens is, because I added reactants, okay? And then, because it's a reactant, same thing, I'm going to decrease, okay? I'm going to disappear over time, and then I'm going to flatline. And now this is my new equilibrium. So when you see these diagrams on the AP test, and you see how you were at equilibrium, but then something changes and then goes back, that means you had a stress. Something changed, okay? So notice also at this equilibrium, you're at this value, whatever this concentration is. But this new equilibrium, if you drag this line about, okay, you're at a different concentration. So this new equilibrium is because I added more reactants. So what about the products? Okay, so I was at equilibrium, okay, and because I added reactants, what do I have to do to fix equilibrium? Well, I had to shift to the right by adding more products. So look at what happened. Because he's a product, what's a product doing over time? Well, he's appearing. So I had to shift equilibrium, and so that means I had to add more product, and he's appearing over time, and then I get this new equilibrium. And notice the difference. That equilibrium in the beginning versus this new equilibrium. Why such the big amount? Is because to fix the equilibrium, I had to add more products. Okay, so chapter 14, disappearing versus appearing, is still valid with equilibrium. how did you fix it and what happened to this new equilibrium, you need to make sure you understand that with these equilibrium diagrams. So over here, I'm appearing my products, and right here, my reactants are disappearing, okay, over time. But regardless, I have a new equilibrium that's been established after I shift. Also notice right here, because I have twice the moles, I am disappearing twice as fast. So this times 2, it's because it's disappearing 2 times faster. This one is appearing, okay, I guess you can say half the speed, half as fast as that concentration, okay? So make sure you understand what that 2x versus x is, okay? So the point is, what part of what part of K is getting affected, and how do you fix it? But remember, this Kc value does not change because temperature stayed constant. It's this guy that you're solving for, because remember, Q is at any point in time, but not equilibrium. And by adding that reactant, I'm not at equilibrium no more because I disturbed it, okay? Well, on the flip side, what happens if we add more products, okay? So if this is my reactant, my 2NO2, and this is my N2O4, I added products, still constant temperature, and I've applied a stress. So since the concentration of NO2 increases, notice the brackets in the K. My numerator now is bigger. So I was at equilibrium. I added products. And now I am not at equilibrium. Okay, I have disturbed equilibrium. I added a stress. So now I have a big number divided by a small number. Big number by small number, my Q is actually, it's going to get bigger than my K. So since my Q is now greater than my K, I have this scenario. So using my cool arrows, how do I need to fix equilibrium? Well, I need to add more reactants. And because the reactants are on the left side, I got to shift to the left. And by shifting to the left, so that way Q equals my K. Okay? So that's the scenario of Le Chatelier's. Okay? If you actually remove some reactants, don't get tripped up by removing. Okay? So if I actually remove some reactants, what does my teeter-totter look like? Well, remember this was my reactants and products, but I lost some reactants. So isn't he kind of now floating in the air? Which looks kind of like that scenario right there, okay? Same thing, okay? So because I removed some NO2, look at what happened. Smaller. He got smaller. So I still have a big number over a small number. My Q is still bigger than K. Same thing. I have to produce more reactants. I got to shift to the left, so that way my K equals my Q. Okay. Same thing if I remove some products. Oops, my little teeter-totter. Okay. If I remove some products, well, now my products, they're kind of floating up in the air now. So my reactants and products, how do I fix it? Well, I got to lose some reactants, or tell AP you got to gain. I always like to say when you have to gain more, so I got to produce more products, but you could have said or lose some reactants. Because I have to shift to produce more products, I'm going to have to shift to the right, so that way my K equals my Q. Okay, so notice right here, because I lost some products, small number over big, so my Q went down. Okay, use the cool trick of the arrow. What happens if AP mentions about maybe just adding a random chemical? Like sometimes they'll say, let's add an inert gas. An inert gas is a noble gas. So remember, this is group 18 on the periodic table. Suppose that the system shown above at equilibrium, a sample of He or maybe neon or argon is added at constant temperature. Well, what's going to happen? Well, no effect. And why not? Because where is helium, argon, or neon in your Kc or Q? He's nowhere. So they're already at equilibrium. There's no shift, but that can't be your period. Okay, that can't be the end of the story. There's no shift in equilibrium because He is not in your K or Q expression. So ladies and gentlemen, I took the time to write out the essays, the little explanations for you. That's what AP wants to hear. Do not ever, 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 ever say, because of Chatelier's principle, oh, AP already stopped reading. Okay, don't do that. Instead, talk about how do you fix the change. Q will either be greater or less than K. The equilibrium will shift by either producing or removing. And which way are you going to shift, left or right? And that's the name of the game. How do I get my Q to equal my K? All right. Hopefully concentration wasn't too bad. Hopefully the teeter-totter is a little cool. I will tell you, stress number 2, pressure and volume, usually is a little bit harder for students. Okay. So beware of the pressure and the volume. It's not the teeter-totter. Okay. Let's say we have the same equation, but now I decrease the volume of the container. Anytime that AP says vessel or container, vessel is just whatever you have it in, a cylinder, a box, so forth, okay? Suppose that the system was at equilibrium, and then you decrease the volume. So you had 2 liters, and now you have 1 liter. Well, what happened? Well, back in the day, chapter 10, Boyle's law. If volume goes down, well, pressure goes up, but as long as temperature stays constant, okay? So you applied pressure, okay? You have more collisions, okay? You brought those gases closer together. So you have an increase in pressure, you have more collisions, okay? So what happens is, here's equilibrium's rule, okay? If you decrease the volume of the reaction will shift towards the side with the fewer gas moles, okay? So notice my equation. Which side has fewer gas moles? Well, my product side does, okay? So what happens if my product side has fewer moles? I am shifting in that direction. I am literally going to that direction. So what happens is, which one's bigger or smaller? Well, remember, if I'm going to have to shift to the product side, that means my K must be greater than my Q. So to reestablish equilibrium, the reaction must shift to the side. Tell AP which side you're going to, okay? And I'm going to shift to the side with the least gaseous moles. In this case, I would put in parentheses the product side. And the reaction will shift to the right, so that way K equals Q, okay? What does it actually look like as a particle diagram, okay? Because you're probably thinking to yourself, well, why the fewest moles, okay? So look at the equation we had. We had 2NO2, and then we have N2O4. Okay, so if you notice right here, I have, and I'm just going to circle this part, okay? I have 6 moles of that N2O4, and I also have 6 moles of that NO2. So this guy right here, that's your N2O4, and that is your NO2, okay? Now notice what happens. Volume is decreased initially, so the pressure increases. So you brought them closer together. So the spaces between the gases got closer together, okay? So what happens is, at equilibrium, it's going to shift to the side with the fewest gas moles, so decrease that total pressure. So notice what you did. 1, 2, 3, 4, 5, 6, 7, 8. I now have 8 moles of that N2O4. And notice what happened right there. An NO2 and an NO2. I had to produce more products. And I did. I went from 6 moles to 8 moles. Okay? That's what happened. Okay? So what's AP's rule? If the volume decreases, it shifts to the side with the least gaseous moles. Now notice it says gaseous moles. Not solids, not liquid, not aqueous. It's got to go gaseous moles. Okay? So do not focus on solids, liquids, and aqueous. Kind of just block them out of your point of view. Okay? Well, let's go on the flip side. What if I increase the volume? Okay? Well, according to Boyle's law, volume goes up, pressure goes down. Okay? Which means I went from a maybe 1 liter container to a 2 liter container. I now have more space for those gases to move around. Okay? So according to equilibrium, it will shift with increasing volume or decreased pressure, okay, to the side with the most gaseous moles. And which side is the most gaseous moles? Well, that's my reactant side, okay? So I'm actually going to produce more reactants. So notice my K and Q, if I needed to shift this way, then that means, oops, right there. Oops, I know I had a boo-boo there. All right. Since right here, my K has to be less than my Q, because in this scenario over here, my Q is less than my K. And I got to fix this right here. Oops, bad cut and paste. My Q is now greater than my K, so I need a shift to produce more reactants, so it's going to go to the side with the most gaseous moles, aka reactant side. And I'm going to shift to the left, and why? Because that's where the reactants are. So that way my K equals my Q. Okay? So this is what it looks like. Same thing. I had 6 moles of NO2, and I have 6 moles of, sorry, this is N2O4, and then I have NO2. And I increased volume, so notice the container got bigger, okay? And by increasing the volume, my pressure goes down. So notice what you have. Now you only have 2 N2O4s, and you have, I'm not even going to count all that, way more than 6, okay? So my NO2 is way more than 6 moles, okay? It looks probably like about 10 or 12. Okay, and that's what happens. Okay, so in summary, because pressure and volume changes are really hard for students, focus on the gases. Okay, so only focus on gas moles when looking at pressure versus volume. Okay, if both sides actually have equal moles, then what happens? There's no shift. You're already at equilibrium. Yeah, your Q is already at equilibrium. Okay. This also works for aqueous ions also if we were doing concentration, but let's focus only on the gases. Okay. Changing pressure and volume still does not affect K and Y because we haven't touched temperature. So notice in scenario 1, we didn't touch temperature. Scenario 2, we didn't touch temperature, but now let's mess with the temperature. Okay, change in temperature, now K changes. Okay, so in 2NO2, what happens if I actually change the temperature and make this guy hotter? If I add some heat, okay, to NO2, well, he actually gets darker. Okay, he gets a darker brown. And what happens if maybe I add heat, or actually lose heat, for the NO2? Well, what happens if I put it in an ice bath? Well, the color actually gets lighter. So when we actually heat or cool substances down in the lab, I want you to pay attention to changing temperature. Changing temperature can actually change color, which that is called a chemical reaction, okay? Students always think, well, you still have the same thing. No, that's a phase change. If I actually change color, that's a chemical reaction, okay? So here's the big one. Not only do we have to figure out how we're going to have to shift, but now what's going to happen to my K? So changing the temperature will affect K. Will K increase? Will it decrease? Or we like to call no effect, okay? So in summary, before we practice, if you have endothermic means you added heat to the reaction. You have to think of heat as a chemical, okay? Think it's a chemical. Notice I said the word think, okay? Think it's a chemical. Delta H, okay? Delta H is something called enthalpy, which we talked about in chapter 14. This is going to be big when we get to chapter 5 and 19, thermodynamics. Enthalpy is heat, okay? So if I said endothermic, my delta H just has to be greater than 0. Just has to be positive, okay? So if I added heat, I need to actually write the word heat as a reactant. So notice if I increase the temperature. So there's my heat, there's my temperature. So if I increase temperature, my teeter-totter looks like this. And why? Because heat is a reactant, okay? So how am I going to fix it? I got to shift, okay, to the right. I have to form more products. Okay, so that way my K equals my Q. But now let's talk about the beast. Why is K going to increase? Remember, your K is products of the reactants. Okay, who is increasing? Who are you affecting by fixing equilibrium? Okay, so actually I'm going to get rid of, no, I'm not going to do that yet. All right, let's have it a moment in my head. Okay, I'm going to form more products. So because I'm going to form more products, what's going to happen to this value in the numerator? He's going to get bigger and bigger and bigger, and this R is going to get smaller. What's a big number divided by a small number? Well, K is going to increase. It's going to get bigger than what it originally was. Okay, so this is where you can kind of think, well, isn't this Q? But yeah, remember, I'm trying to reestablish equilibrium, okay? So my K will increase. Well, now think of it as, what if I decrease temperature, okay? Well, remember, let me put a little space right here. Oops, space. Put my little triangle right there, okay? So if I had equilibrium, but now my heat, I'm taking heat away. So that means my products just got very dominant. So to fix equilibrium, I'm going to have to shift to the left. And what do I have to do? I have to produce more reactants. Oops, reactants, okay? I have to produce more reactants. So now what happens? Products of the reactants. I have to produce more reactants. So my denominator is getting bigger and bigger. What's a small number divided by a big number? Well, it's going to go down, okay? I'm not asking you to calculate the new K. Can you just tell me what happens to K as it goes up and down, okay? But only if you change temperature, okay? Next scenario, I'm going to change it into blue, okay? What if it's exo? Well, exo means you lost heat. You're removing heat. So now heat is like a product. Okay? Remember I said the word think. It's a product. Like it's a chemical. But remember, heat is antimatter because it's energy. Okay? It's not matter. Energy. So if it's exiting, my delta H, that just means it has to be negative. Okay? It just has to be less than 0. Okay? So whatever this delta H value is, just negative. Okay? So teeter-totter. Okay? So if I increase my heat, I'm increasing my heat, which is a product. So that means my products just got very dominant. And my reactants are kind of sitting up here in outer space. Okay? So what do I have to do? I have to produce, shift to the left. I have to produce more reactants or lose some products. Okay? And remember, K is products, so the reactants. And my reactants are getting bigger and bigger and bigger. So what happens? My K is going to decrease. Okay? On the flip side, if I remove some heat, okay, so now my heat, oops, I'm taking the heat, and that means my reactants are very dominant. So what do I have to do? Well, I'm going to have to shift to the right. I'm going to have to produce more products. And my K, because my products are getting bigger and bigger as my reactants are getting smaller, and big number divided by small, what's going to happen to my K? My K is going to increase. Okay? Students actually do very well with the temperature part. It's pressure and volume that are always the trickiest. Okay? So we have 2 practice problems, but here's kind of like a little summary, little Cliff Notes version, so that way you can help remind yourself. Okay? Last stress. What happens if you add a catalyst? Okay? A catalyst does 4 things. Okay? It lowers EA. Okay? It provides an alternate route to get there. So remember in chapter 14, when we had our activation diagrams, remember a catalyst starts and begins in the same spot. It just lowers our EA. So that right there, that's from my catalyst. Okay? Remember, it also speeds up the reaction. Okay? And remember, catalyst is never in the balanced equation. So if it's never in the balanced equation, it's not in the K or Q expression. So if it's not in K and Q, then it doesn't affect equilibrium, okay? Because it's not in the K or Q expression, okay? So a catalyst does changes, but not to equilibrium, okay? So let's do some practice scenarios, okay? And we're going to practice explaining too, and I'll try to get my typing so that way you guys can read my crazy writing. So first, let's analyze the equation. I have a gas and produces 2 other gases. I know my delta H right here is positive. It's greater than 0. So that just told me endothermic. I'm just making some notes. Okay. So we have 5 scenarios. I want to know which way it's going to shift to fix equilibrium. What will happen to K? So let's do a little reminder. K only affected by temperature. Okay. So if I notice any of these, Cl2 is removed. Well, that doesn't affect K. Temperature's decreased. Okay, something's happening there. Volume, nope, not changing. PLC's added, nope, not changing. And temperature's increased. All right, well, I got 2 temperatures there. Okay. I always like to do those first because I don't want to get tricked in the head thinking K is going to change unless it's temperature. Okay. All right, Cl2 is removed. So Cl2 is right there, and he's removed. So I use my little teeter-totters, okay? So because Cl2 is a product, okay, I'm going to have to shift to form more products, okay? So how do we write this, okay? So to achieve equilibrium, okay? I don't know why it doesn't like the word re-achieve. Oh, maybe that's why it's because it's not a word. Huh? Or re-establish, okay? So I'm going to say right here to re-achieve. That's probably like a really bad re-establish. I always like to use that word too. to achieve or reestablish equilibrium, the reaction must produce more products. Like I said, you could also say lose reactants. Please don't write both. It's kind of overkill. And shift the reaction to the, looks like right side, so that K equals Q. Ta-da! There you go. Okay. All right. Temperatures decreased. Okay. So because this is positive, endothermic, I'm going to add the word heat on my reactant side. So add the word heat. If temperatures decreased, where's my heat? Well, my heat is a reactant. And because my heat is a reactant, it's losing heat, which means my heat is right here. Okay? So the endo part is because you have to add the word heat as a reactant. What the heat does, well, that depends on the scenario. Okay? So if my heat is here, how do I fix it? Well, I'm going to have to shift to the left. So it's literally kind of like the same scenario, but we're just going to change some words instead. Okay? So to re-establish equilibrium, the reaction must produce more reactants. It's the same essay, just changing other words. Or you could say less products. And I'm going to have to shift to the right. I'm sorry, I'm going to have to shift to the left. So that way K equals Q. Okay? But now here's the big one. What happens to K? Because I have to produce more reactants. My K, products over the reactants, I have to produce more reactants. My reactants are getting bigger and bigger and bigger. Excuse me. So products over reactants, small number over big number, my K is going to decrease. Okay? It's not going negative, people. I don't remember, K is never negative. Okay? But it's just going to go down. Okay? So I'm going to make that note right there. K, and then K, never negative. Okay? It's just going down. All right, volume of the system's increased. Okay, so volume of the system's increased, which means pressure is going down. Okay, but what are we looking at? Well, remember, if volume is increased, let's go back in the notes. That was decrease. All right, increasing volume is going to go, it's going to shift to the side with the most moles of gas. Okay. So most moles of gas, well, which side has more moles of gas? Well, this has 1 mole of gas, and this has 2 moles of gas. So I am shifting, I'm just making notes, I'm going to shift to the side with more gaseous moles. And which side is that? That's the product side. So when you're doing volume and pressure, it's not a teeter-totter. You are going to that side. I'm going to the product side, which means my shifting is happening this way, and my K, there's no effect. Okay? Well, if you look right here at this scenario and that scenario, there you go. We just have to fix a little bit of wording. So I'm going to copy that and put it right here. Oops. See what happens when you try to do shortcuts? All right, to reestablish equilibrium, the reaction must, we're going to say, shift to the side with the most gaseous moles. And I'm just going to put in the parentheses, I'm going to just say product side. There you go. Which means it's going to shift. We're going to fix our language here. the reaction must shift to the side with the most gaseous moles, aka product side. Whoops, product side, not produce side. Which is shifting to the right side so that K equals Q. Now I notice I just put the word to, so oops, I know you're yelling at Rodriguez right now. All right, let's fix our AP language here. To achieve equilibrium, the reaction must shift to the side with the most gaseous moles, product side, which is shifting to the right so that K equals Q. All right, easy peasy, okay? PCl3 is added. Well, PCl3 is a product, okay? So my PCl3 is a product, which means my teeter-totter, PCl3, looks like this, okay? Well, just like scenario letter B, looks just like that. So that means I'm going to have to shift to make more reactants. My K is not changing, so I'm simply just going to take this and put it right there. Get rid of that letter E. There you go. To reestablish equilibrium, the reaction must produce more reactants and shift the reactant to the left, so that way K equals Q. Scenario E, increase in temperature. Okay, well, now I still have endothermic, and I still got heat on the reactant side, but now I'm increasing it, okay? So which means my heat is over here. So if my heat is over here because I'm increasing the heat, I'm shifting to the left, okay? Well, it sounds just like scenario A right here. Now, I'm not going to copy and paste C, because C has to do with shifting with the most gaseous moles, okay? Not looking at that. So I'm taking that scenario, putting it right there. There you go. Now what happens to K? So K will change. So because I have to shift to produce more products, and more products of the reactants, big number over small number, big number over small, that just means my K is going to increase, okay? So I want you to try a scenario, okay? Number 2, new equation, and explain, okay? You have gaseous moles, but now you have a delta H that's negative. And because it's negative, that means exothermic. You're losing heat. And because you're losing heat, you have to think of heat as a product. Okay? So same thing. Which way does it shift? What does K do? Pay attention to the temperature ones. Okay? So if you do this right, there should be only one of these on here that changes K. And then go from there. Okay? At the end of the video, ladies and gentlemen, there are plenty of practice AP exam, former AP exam free response questions. All right, see you on the next one.